Yeah. All right, are there any questions before I begin? Yes?
Yeah, on number 13 on the homework.
Okay.
The first point that it plots.
13.
It should be 0 and 40 is the correct answer, but I don't understand how.
Are you talking about the rechargeable battery? Are we talking about the same thing?
Number 13 from the homework.
2.1, 2.2, sorry. Let me see. The graph?
I don't know how to get that with my eyeballs. Without any reference, I don't understand.
You're talking about the one that's this little graph right here?
Yeah.
Yes, and it wants you to like...
It wants me to plot 0, and the correct answer is 40, but I don't understand how to get that without any reference.
Okay, I think what I'll do is I'll bring the problem up so we can all see it, all right? Let me do that real quick. Give me a second. Talking about this one right here, right? Okay. Looking for a zoom here. I don't see a zoom, so let me do this. I know there's a zoom somewhere. I can get the whole problem. Let's do it this way. Number one, I'm glad you're doing your homework, okay? This question is frustrating because you're supposed to estimate something, and so I think it's subjective. We could argue, we can make different arguments, but I think we should all get something close to the same answer. So it says, a rechargeable battery is plugged into a charger. The graph shows C of t, the percentage of full capacity that the battery reaches as a function of time. So you plug in your phone, it's dead, right? You plug it in, you got 0%. And then as time goes on, it starts charging, and it kind of flattens out and gets closer to 100. What they're wanting us to do is first figure out what is the meaning of the derivative, right? So if we talk about, what is the meaning of the derivative of that function, remember that the derivative is a slope of a tangent line, right? Slope of a tangent line is rise divided by run, right? So I'm going to write that down. C prime t is the slope of the tangent, but that in turn is rise over run at specific points along the graph, right? We can find tangent lines. For us, the rise, this y coordinate, is a measurement of percentage, right? A percentage of charge. So our rise is always going to be measured in percent, and then we're dividing that by the run, which is a measurement of time, in this case hours, right? So percent per hour. What they're trying to get you to see is that the derivative gives you a rate of change of percent to time, or the proportion percent, like miles per hour, right? Like miles over hours would be miles per hour. This is going to be percent per hour. That's the meaning of the derivative. It gives you a percent per hour at any particular point on the graph. Then it says to sketch the graph of C prime of t. Is this the part that you're, yes? Okay, so this is what last class was about, right? We go to the graph, let's see if there's anywhere we can agree upon. What do y'all say? Somewhere around here, if I do the tangent line here, Would you all agree that looks like it's about a slope of 1? Like you go up the same amount you go over? Yeah?
So
Yes?
how do you know like what the slope is just by looking at
I'm estimating, right? But first, if I go here, do you agree it's positive? We have a positive slope. Now remember slopes, 0, right? 1 is a perfect diagonal. 2 is steeper, 3 steeper, 4 steeper. It doesn't go like this, it doesn't go over like that. The bigger the number, the steeper you get until you get vertical. And vertical means you have an infinite slope, right? Actually, the slope is undefined. So if you had a slope of, let's say 100, it would be, a slope of 100 would be really, really steep. Not quite vertical, just a little bit over, all right? A slope of 1,000 would be just a little bit more. 1,000,000 would be almost vertical. It's kind of a weird concept. I mean, think about, if I tell you that the slope is 1,000,000. 1,000,000 is the same as 1,000,000 over 1, right? So that means the slope is rise is 1,000,000, run is 1. So you go up 1,000,000 and move over 1. That's pretty steep, isn't it? See what I'm saying? Okay, so I'm estimating, I'm just looking at the graph and I'm trying to look for a point that I think the slope is about 1. That's what I'm looking for. And I think it's about there. I mean, you could argue it's somewhere near here, but you can't come over here and tell me the slope is 1. Do you all agree? Yeah? Okay, and then, so if I'm trying to graph the derivative, right, if I'm trying to graph the derivative, what I know is that about at this point here, I'm going to say about right here, my slope is positive 1, whatever you want it to be, but what's happening as I go this direction? Is that slope going to get steeper, or is it going to like flatten out, get closer to 0? Closer to 0, right? The slope is getting closer to 0. So that means when I draw my derivative, this should be getting closer to 0 as I go to the right. Now I'm never actually going to get to 0 because this doesn't actually flatten out, right? Completely. What happens if I go this direction? What's happening to the slope? Steeper and steeper and steeper, right? And we just said that the steeper the slope is, the bigger the number is. And they're all positive. So I'm going to look, the derivative's going to look like that. So this is c prime of t. Okay? Does that, yes, no? I can't tell by your...
where it's like curved down there?
Down here?
Yeah.
Okay, if I go out here to another point, right? I go up there and I ask, what's the slope of the tangent line? You would tell me it's positive, right? But it's a smaller number than this number, right? Because that's, we said the slope here is, you know, some positive number. If I move here, that's still positive, but a smaller number, right? So here's that first point that corresponds to that slope. If I move over a little bit, well, pretty far, then you told me that's going to be a positive number, but smaller. Do you agree that this dot right here is a positive number, but smaller than that one? And the further I go that way, I'll stay positive, but I'll still be getting smaller. So all these points are smaller and smaller positive numbers. That make sense? Everyone got that? Okay, I don't know if I answered your question, because you said something about 40.
Yeah, they have like answers.
Yeah, let me see what they're...
It just seemed crazy that they had 40%.
Oh, wait, hold on, I need to go back. Instantaneous rate of change, okay. Are you talking about like they had 40 at 0?
Yeah.
Okay, we don't need, okay, so for us, we don't need to really make that graph be accurate. All I want is this. You just want the behavior of the function, because everything is hard to read. I mean, we're just reading a graph. They're not giving us the specific function. So we just want the behavior of the derivative. You don't need to label things and make it, you don't need to make it go exactly to that point. That's okay.
I think what messed me up is like I was plotting it. I was doing a relative run.
Uh-huh.
And like, you know, I think I was getting like 1 or 40 over 1, 30 over 2.
Like you were actually getting like actual, like these values, you were trying to figure out what those were.
Yeah, I was trying
Yeah.
to, but I didn't know how to use 0 because it's at the bottom, so like I don't have like a reference to
Yeah, they don't,
that number.
They don't do a good job on this graph of drawing. This implies that this goes on forever and there's asymptote here. And then this is hard to tell what they're saying here because the original graph isn't very good. We don't know if we have a vertical tangent line there or not. It's hard to read this and tell whether or not this goes completely vertical or if it's got a little bit of a slope to it. So I think this is more of just a estimation problem. Is that all right? Okay. Good questions, good questions. I won't give you a problem like this on a test. What I would do is give you a graph that's not labeled, like I wouldn't label this, just like we did in last class, and I'd ask you to draw the derivative. In fact, I was going to give you a quiz today, but I had some students that said they had questions about this still, so I didn't want to give a quiz. We will definitely have a quiz next class. And what I'm going to do is I'm going to take the review for the next exam, and I'm going to take a few of the problems off the beginning, which is I draw a function, you draw the derivative. And that'll be your quiz next class, all right? And then there might be some more to it, but that's definitely going to be on there. Okay, may I proceed? Yes? All right, so I was looking here at the video from last class, and what I wanted to do was, we're about to get into the next section. I wanted to look at this problem that we did in class, all right, where I know you can't see it much, but we worked this problem in class last time, and what it was the function 3x squared minus 5x, and I asked you to find the derivative of this. And we went through all the work, all right? And the work we did was, let me see, where am I? So I go in here, I use the formula. I'm using that formula that we wrote on the board. We have to do a limit, right? And we start cranking this thing out, and eventually we get to a point where we cancel things, and then eventually factor out an h. We're going to cancel an h here. And then we finally, at some point here at the end, where is it? Right here, we finally get to this answer, right? 6x minus 5. So the derivative of this is 6x minus 5. So up until today, right, this is what it would take for us to calculate a derivative, right? That's what it would take. Today, we get the basic differentiation formulas. They're the formulas that are going to allow us to do derivatives without the limit. That's what I promised you last time, right? And so there's a bunch of formulas I'm about to give you. Before I give you the formulas, I just want to show you how quickly I'm going to be able to get this answer using these formulas. Without showing the formulas, I'm just going to show you how to get from here to here. And then we'll actually formally write down what the formulas are. So starting out with this function f of x equals 3x squared minus 5x, when I find the derivative, and again, keep in mind, I haven't taught you this yet. I'm just showing you how fast it is once you learn it, all right? What I'm going to do is I'm going to realize that I have two terms, right? Terms are separated by addition and subtraction. Whenever you have multiple terms, what you can do is look at each one of them individually. So I'm first going to look at this one. And this is x to a power. And we're going to have this thing called the power rule. And what the power rule tells us is that anytime we want to take a derivative of something with x to a power, all we have to do is take that power, bring it out front, and multiply whatever number's out here. So if I bring 2 and I multiply times 3, what do I get? 6. And then the rule says then you write x, and then what you do is you take that power and you reduce it by 1. You subtract 1 from it. So if I take 2 and subtract 1, I get 1, right? And now I'm going to do the same thing on this one, okay? Oh, and I put a minus sign between them. And on this one, I'm going to look at that one by itself. What's the power on x here? 1. Okay, so let's play that same game. 1 comes out, hits the 5. 1 times 5 is 5. And then it would be x to what power? 0, right? Because I subtract 1 from that. And then what I realize is this is just 6x minus 5. And now x to the 0 power is 1. So this is really like 5 times 1. And I'm done. You see? That's the same answer. It's not coincidence. That's what the rules allow us to do. So that's a lot better than the limit, right? We can do it, really quick. Let's do another one without me formally giving you the rules. Let's do another one, see if you kind of catch on to this. All right, so let's do f of x. Let's do negative 3x to the 7th plus 4x squared plus 3x. All right, so let's try this. So we have 3 terms, right? 3 terms. So I'm going to do them individually. Let's look at this one right here. I'm going to write the derivative of this is equal to, all right, who wants it? Raise your hand. Go ahead. Yeah, I'm there, right? Okay.
Is it
Negative 21. Okay, so you're multiplying 7 times negative 3. Good. X to the power of 6. Done, right? Everyone see that? You like this, don't you? This is better than the limit, isn't it? All right, next one. Who wants the next one? Go ahead. Plus 8x, right? So the 2 comes out, hits the 4, becomes an 8. You subtract 1 from x, or from 2, you get x to the first power. All right, who wants the last one? 3? Just 3. Okay. So look at this one. You can look at that as a 1 that comes out, okay, and then this becomes x to the 0. You can look at it that way, or you can just remember that whenever you have the derivative of x by itself, that turns into a 1. So when you take derivative, this just becomes 3 times 1, which is just going to be 3. Got it? Now, I want us to appreciate what this formula is saving, what these formulas are saving us from, right? Because if you didn't have that formula, the shortcuts, then if I asked you to do that problem using the limit definition, here's what it would look like. We're not going to do it, but here's what it would look like. We would do limit as h goes to 0. The formula I wrote on the board last time. We would first have to write this, but replace all the x's with x plus h's. And then what we would have to do is subtract from that f of x, which would be negative 3x to the 7th plus 4x squared plus 3x, and then divide the whole thing by h. That's what we would have to do. And that would suck. Yes?
Is there something that would not allow us to do that shortcut?
Well, the problem is the functions are going to become more complicated, right? So it turns out if it's a polynomial function like this, we're going to be happy. But if it's something more complicated, then what do, right? So we're going to have a bunch of rules. Right? No one wants to do this, right? Who wants to do x plus h to the 7th power, right? Multiply it 7 times itself. Do all. No one wants to do that, right? So luckily, we don't have to. All right, let's formally go through the rules. Now we need to take a vote as a class, all right? With these rules, I can either prove each one of them to you, or you can just take them on faith. I'm open to doing whatever you as a class want to do. Like, do you want me to prove to you that you can do these things?
It's
Yeah.
important in the long run, but we know how they are.
You don't need to know the proof. Now, if you're a math major, at some point you would. Like, you would have to actually go back. Let me mute this real quick. Okay. What do y'all think? How about this? How about I'll do one of them, okay? And then that's it, just one. And then the rest you can just believe, yeah? And if you want to see them proven, I would encourage you to come to my office and we can sit down and go through the proofs, all right? So let's take a look at our first formula. Now, this right here is new notation that we had from last class. When we write d over dx, that means take the derivative. I want to find the derivative. Okay, so this is saying, hey, take the derivative. We're treating x like a variable here, and what I'm doing is trying to take the derivative of what? A constant, okay? So what happens if you have a constant function, and you want to know the slope of the tangent line. That's what this is saying. I'm going to prove this one just visually. This is an easy thing to convince students about if you just let me graph it. So let's say I have a function f of x equals c, which is a constant. That's going to be a horizontal line, right? It's going to be a horizontal line. So like if c was, let's say, 3, I would move up 3 and draw a horizontal line. Here I'm going to draw just a horizontal line like this, and I'm going to say that it passes through here at c. Does everyone agree that no matter what point you go to on this graph, go to any point, go to any x value, go up to that point, that the slope of the tangent line would be 0? Go to any point, go up there, slope of the tangent line would be 0 all the time, right? So does it make sense that the derivative of a constant is 0? Yeah? All right. Yes?
Did you remember to unmute?
Pardon?
Did you remember to unmute?
I think I'm unmuted. Yeah, why was I muted in my last
No, I
one?
just want to make sure.
Yeah, I don't know if I'm recording. Is there a red dot on that little screen up there? Yes?
Screen or on the little thing?
Not on the thing on the bottom. Like you see the little window where it shows me? Is there a red dot there? Up in the top? No? I'm pretty sure I'm recording. No? Oh, it's hard to see it. It's there. There's a thing I can do where a red dot will show up over here somewhere, but it's on. I'm good. Okay, so are y'all okay with that? The derivative of a constant is 0. So let's just do a couple of really quick examples. If I had f of x equals 5, and I ask you for the derivative of that, you would say 0, right? That's it. Derivative of 10, 0. Derivative of pi. Pi is a constant, isn't it? What's the derivative of pi? 0. Okay? So that's our first rule. The next rule says that if you try and take the derivative, treating x like the variable of the function x itself, you should get 1. I can show you this visually as well. Let me graph for you the function f of x equals x. Now, hopefully in college algebra, you were told that this is an important function. It's actually called the identity function. It's called the identity function because whatever you plug in is exactly what comes out. It's identical, right? You plug in 4, it spits out 4. You plug in 2, it spits out 2, right? Whatever goes in comes out, unchanged. So you graph this, you plug in 0, you get 0. You plug in 1, you get 1. You plug in 2, you get 2, right? So if you draw this, you get the diagonal line, right? That perfect diagonal line. And do you see again that if we go to any point on this graph and look for the slope of the tangent line, it's going to be the same as the slope of this line. So if I go to any point x, go here, slope is that, whatever that slope is, right? But what is that slope? What is the slope of a diagonal line? Perfectly diagonal line. 1, right? You can tell because this looks like, remember the y equals mx plus b? The number in front of the x is going to be your slope, right? So the slope of this line is 1, which means the slope of any tangent line would be 1 as well. Make sense? So the derivative of x is 1. Next rule. Okay, the power rule. So I'm going to write down a couple of examples. This one I cannot prove to you visually. So this is the one and the only one I'm going to do the proof on, all right? The previous two I did visually. I think we're all okay with that, I think. This one, I unfortunately cannot do a picture, but I'm going to show you the rule a few times first, a couple examples, then I'll do the proof. All right, so for this one, what this rule says that is if you've got f of x equals, let's say, x to the third power, that the derivative of that, according to this rule says if you ever want to take the derivative, treating x like your variable, of x raised to the power n, What you're going to do is you're going to bring that n out in front, and you're going to subtract 1 from the n. That's what I just told you a minute ago, right? You bring that number out and you subtract 1. That's what the rule says we are allowed to do. So for this, we would get 3 comes out front, x, subtract 1 from the power, we get 2. Okay? I haven't proven the rule. We're using it, right? Practicing with it. You okay with that? All right, what about this one? Now that's different, right? Because you have to ask yourself, can you use the rule? Well, is this x to a power? Yes, what power? A half. So everyone here has to be comfortable with the idea that the square root of x, well, let me give you the rule, let me give you the property back from college algebra, that if you have x and you take a root, right, the nth root of x, that's the same as x raised to the 1 over n power. This is a very important property that we're going to need here, right? That if you ever have whatever the root is, you create a fraction out of it. And there's an even better formula than this that looks like this. If you have the nth root of x and you raise that x to the m power, that's equal to x to the m over n, like that. This one is the one that we really want to be more comfortable with because it allows us to handle any root and any power in here on the x. We can rewrite it as a fractional power. So in college algebra, you're taught about these. Well, hopefully you're taught these formulas. And I don't know if your teacher told you back then, the reason why this is so important is because when you get to calculus, we prefer this, right? We prefer this because then we can use that rule, all right? If we can write x as a power, we can use this power rule. So let's see about taking the derivative here. If I take the derivative, all right, who wants to tell me what I'm going to do? Don't tell me the answer, but just tell me what I do. Raise your hand, please. Who wants? Go ahead. So what am I going to do? Okay, move the 1/2 to the front, and then write x, right? And then? I'm going to subtract 1 from that power, right? So let me just write that down. I'm going to take the 1/2, and I'm going to subtract 1. So you've got to be able to subtract fractions here, right? You have to take the fraction 1/2 and subtract 1. That is a college algebra, pre-college algebra idea, right? That's like a pre-algebra. We're subtracting fractions. So as a reminder, because I know this is, in doing this for so many years, I know this is one thing that hangs students up. Look, all you're doing here is rewriting the 1 as 1 over 1, and then getting a common denominator, so you're multiplying the top and bottom of this fraction by 2. And now, because they have the same denominator, you just do 1 minus 2 over the common denominator, and that's negative 1 over 2. That's how we subtract 1 from a fraction. Believe it or not, you're going to get good at this, and you're probably going to get to a point where you just do it in your head, because you're going to have to, because it's going to take too much time to do this every single time. But here's where we are. We have 1 over 2 x to the negative 1/2. Y'all good with that? Now, I'm done. That's the derivative. I'm done. But I want to point something out. Do y'all remember that whenever you have a negative exponent, it means you can drop it down to the denominator? Like if you wrote down x to the negative 2, that's the same as 1 over x squared. That negative exponents drop down. I'm going to rewrite this as 1 over 2 times 1 over x to the positive 1/2. See how I changed it from negative to positive, but I dropped it down? Yeah? But what is x to the half? Square root of x, right? So this is 1 over 2 square root of x. What I did there is I turned that into a square root of x, and then I put these fractions together by multiplying straight across. And I get this answer right here. Questions on that? I'm going to leave that as my answer. I want you to put a star next to this one. No, let's do 3 stars. Let's do 4 stars next to this one. Because as a Cal 1 student, we are going to take a derivative, we're going to take the derivative of the square root of x so many times in this class that what you should do is just burn into your brain that the derivative of the square root of x is 1 over 2 root x. The derivative of the square root of x is 1 over 2 root x. The derivative of the square root of x is 1 over 2 root x. Just burn it in, all right? There's others that we'll do that aren't as common, and I won't ask you to remember those or memorize them. You'll just go through the formula. But that one just comes up so much that we don't have time to do this every single time on the square root of x. Let's do another one. I still haven't proven this, right? I still haven't proven that formula. You're just taking it on faith. Okay, next one. How about this one? Ooh. Okay, we have a major issue to talk about here. Right now, as it sits in this class, you only know how to take the derivative of a constant, right? The derivative of a constant is 0. You know that the derivative of x is 1, right? Those are the two previous formulas. And then I've given you this power formula, power rule, that only allows you to take derivative if you have x to a power, right? This, yes, I agree, that is x to a power, but do you see that you have a fraction here, right? You have 1 divided by this. I have not told you anything about how to take the derivative when you have fractions. Only x to a power, or constants, or x by itself. So if you're going to use any rule that I've given you, like this one, you're going to have to rewrite this as x to a power. So I'm going to rewrite this first as 1 over x to the half, okay? And then, I'm not doing any derivative right now. I'm just rewriting it algebraically. I'm going to bring that back up as x to the negative 1/2. Do you all agree that that expression is exactly the same as that expression? Yes? You all see it? Now, is this x to a power? Yes. Can I use a power rule then? Yes. So let's do the power rule. So the derivative of this, the derivative of that f, will be, okay, who wants this one? Go ahead, what am I going to do?
You're going to bring the negative half up front,
Okay, there we go.
and after that you're going to write x,
Okay,
and then you're going to subtract 1 from the 1/2, giving you
oops, yep.
negative 3 halves.
It gives you negative 3/2 x. Let me go ahead and just write that all down. Oh, you already did it, right? Okay. Very good. So we brought the negative half out front. We subtract 1 from that number. So negative 1/2, you take away 1 is the same as negative 1/2 taking away 1 over 1, which is the same as negative 1/2 taking away 2 over 2. And then you do negative 1 take away 2, right? Negative 1 take away 2 is negative 3 over the common denominator of 2. And that's how you get this. You all with me? Yeah? Okay, I'm going to leave this answer as it is.